very interesting for quantum coherent science. So I encourage everybody to show up to that. So today, we're fortunate to have away from Campbell Hall, our very own professor of astronomy, Chung-Pei Ma. So Chung-Pei did her undergrad at MIT. She with Alan Guth and Edmund Bertschinger, is that right? On her PhD thesis. She went from there to be a prize postdoctoral fellow at Caltech, and then joined the faculty at the University of associate professor before we were fortunate enough to have her join us here at Berkeley in 2001, I believe. Is that correct? So, Simon's Fellow, if I remember correctly, right? And she also won a very prestigious award in 2003. I'm just going to read the description for that. Maximally embarrassed before we start. The citation reads, for important contributions to theoretical astrophysics, particularly in the areas of relativistic evolution of density perturbations, testing of structure formation models with massive neutrinos, and the clustering and dynamics of dark matter halos around galaxies. None of which I think you're going to talk about today. I talk about black holes, so please welcome Chung-Pei Ma.
And thanks for giving me the chance to share some recent results with you. As Steve alluded to, I will not be talking about dark matter, dark energy per se today, but I will talk about something dark, and that's black holes. And I will not be talking particularly about theoretical work that I have been doing in the past, but rather this would be mostly an observational project that I started maybe 5 to 8 years ago, and it's still going. Okay. So I would like to talk about supermassive black holes. And to start, I think it's obligatory when the words black holes are mentioned these days to show the LIGO results. You've all seen this in the wonderful talk in the Segre lecture by Ray Weiss, the LIGO's first event. And I just want to highlight that these are the black holes that I will not talk about. And they are the results of the death of massive stars. In this particular case, 2 massive stars that were in binaries. And upon their deaths and final coalescence, they captured this incredible event. But I just want to point out that the masses of these black holes we're talking about are on the order of tens of solar masses. And they are puny. Okay, so, but this gives incredible evidence for the existence of black holes. Okay. But for today's talk, I will like to move on to the sort of second category of astrophysical black holes. And these are called supermassive black holes. And they are in some ways the less mundane type of the 2 types of black holes that we think exist in the universe. And the best example of supermassive black holes is the one residing at the center of our own Milky Way. And here is an infrared picture of our own galaxy. You can see that toward the center, there's a spheroidal component called a bulge. And at the center, there is a supermassive black hole, which had been measured to beautiful precision in its mass by both Andrea Ghez' team at UCLA and our own Reinhard Genzel here. And the mass is at about 4 million solar masses, much, much bigger than the tens of solar masses that LIGO experiment is sensitive to. But this is at the pretty much the low end of the supermassive black holes I'll be talking about today. Okay, I would like to talk about the very, very massive end of this type of black holes. And just for some numbers, the galactic center is at about 8 kiloparsecs away. And so if you compute the event horizon, the the short radius of a 4 million solar mass black hole at that distance, this black hole subtends an angular size of 10 microarcsecond. And this sounds tiny, but it's big enough for very long baseline interferometer to actually image. So I'll talk about very briefly this Event Horizon Telescope that's ongoing in an attempt to image the event horizon of our own Milky Way black hole. Now, moving beyond our own center, then you have to really go to other galaxies, and so I'm at a much greater distances now. The best known example probably is the one at the center of the giant elliptical galaxy Messier 87. And this is the anchor of the so-called Virgo cluster, a cluster of massive galaxies and other galaxies at a distance of about 16.7 megaparsecs. Okay, so we're out to our sort of neighborhood outside of the Milky Way now. And you can see the measurement of this black hole is at 6 billion, okay, much, much bigger than the 4 million at the center of our own galaxy. Of course, this galaxy is a monster. It's a much bigger galaxy compared to the Milky Way as well. And I will talk later that it seems like bigger black holes are living in bigger galaxies, and that's a very exciting correlation people have found. Okay? But just putting this in perspective, at this distance for a 6 billion solar mass black hole, the short radius scales linearly with the mass, then this event horizon actually subtends a very similar angle as the Milky Way, which is much smaller but much closer. So this is the second target for the Event Horizon Telescope because they can resolve this angular size also. So for about 30 years, M87 had been the record of the most massive known black hole. And here I mean nearby. There are a number of quasars at higher redshifts that have been seen, and there are indirect mass measurements for their masses. But here I'm talking about nearby objects where we have direct dynamical measurements using luminous tracers to infer its mass. These measurements tend to be more reliable, but there are only about 100 known so far. And this had been the record holder for 34 years. I want to highlight this paper from 1970s. I don't think their data were really that good to actually detect the black hole. There's indication for that, but remarkably, they got the mass right. 5 billion solar masses in their abstract, and the current latest measurement is 6.3 billion solar masses. Okay, but the evidence was already emerging about 34 years ago. And I will explain briefly why this record held for 34 years until 2011, when my team discovered then the most massive black hole. And this one, you can see now, is at a distance of about 100 megaparsecs. So we are 6 times further out compared to M87. And this is at this so-called coma cluster. It's a much richer cluster of galaxies compared to Virgo. And as more distant, it's much more massive. And NGC 4889, this galaxy is the anchor, the most luminous massive galaxy in the coma cluster. And it's at its center that we found about 15 to 20 billion solar mass black hole, based on measurements of the stellar velocities very close to the black hole. Okay, this is a fairly complicated system, so our error bars were pretty big. So that's why I'm quoting it between 15 to 20 billion solar masses. So it is 3 times more massive than M87, and is 6 times more distant. And I will describe momentarily why this one was fairly difficult to find. And I just want to highlight that earlier this year, my team subsequently found another very ultra-massive black hole here. And this is in the elliptical galaxy called NGC 1600. And this is a cleaner system. So we were able to get a more precise black hole measurements at 17 billion solar masses. And the random error is about 10%. Of course, there are systematic errors on top of this. And so it's, again, about 3 times more. So Given the error bar of 4889, I'll say this tied the record of 4889, although the measurement is a lot better. But this galaxy is closer than COMA, is at about 64 megaparsecs versus 100 megaparsecs. And as a result, the event horizon subtended by such a solar mass black hole, you can see, is fairly comparable to that of M87, and also just a factor of 2 smaller than our own Milky Way. So I think this is providing perhaps a third candidate, a new candidate for the Event Horizon Telescope. Of course, we need to find whether there is observable millimeter emission at the center. Currently, we don't know. It seems very, very weak, very inactive, this black hole. Another striking thing of at the center of a very massive galaxy in a sort of a middle of nowhere, what we call the cosmic backwater. Okay, and just to contrast the two, and that's what I think we got quite excited about earlier this year, is we got 2 now comparably massive black holes. Both are at the very, very high end, but the environments are very different. Again, this is the COMA cluster. Pictures or images are shown on the same physical scale. So you can see COMA cluster 4889 is the big monster here, but it has a twin 4874, almost equal in luminosity and mass. But NGC 1600, the new and it has only very wimpy galaxies as its satellites, as its members. And in total mass, counting dark matter based on dynamical measurements, this group, NGC 1600 galaxy group, is 10 times less massive than the COMA cluster. The X-ray luminosities from ionized hot plasma in the halo is 1,000 times lower, and the galaxies are very different. It's closer. Yet it somehow had a black hole that managed to get to be as massive as 4889. And I think it's still an open question for theorists trying to explain who is feeding these black holes, and how do you make them so massive? Just to highlight a few other examples of black holes, there's a class of galaxies, very active galaxies called Quasars, or active galactic nuclei, AGNs. These tended to be found at very high redshifts. They used to be thought as stars because they're point-like, but now we know they are really at cosmological distances, billions of light years away. And there are indications that their center harbors, some of them, the most luminous quasars appear to harbor perhaps 1 billion to 10 billion solar mass black holes. And this is when the universe was 1 billion years old rather than 14 billion years old. So a lot of questions are out there for theorists to understand how do these distant young quasars evolve into today's sleeping giants like the ones we are discovering. Okay. And here's an example of actual double nuclei. In the X-rays, this is about 1 kiloparsec apart, and this is NGC 6240, so perhaps there are binary black holes in this galaxy system. And I'll come back to binaries momentarily. So just to sort of summarize the very first part of my talk, so why are we studying the most massive black holes and their host galaxies? I just want to remind you that black holes, supermassive black holes, are a fundamental component of a galaxy. There's stars, there's gas, there's dark matter halo, but black holes seem to be ubiquitous. And the ones we've found are at centers of galaxies. Bigger galaxies seem to have more massive black holes. So that's just one component that we would like to study. And also at the most massive end, they are in the state of the evolution of a galaxy's lifetime. So they carry the historical burden or information of cosmic formation. So studying them give you a lot of archaeological information about their past. And they're believed to be products of minor and major galaxy mergers. And also, I mentioned briefly earlier that these nearby quiescent massive black holes and massive galaxies we're studying are probably present-day descendants of high redshift luminous quasars. So understanding their ancestral relationship is a very active field of research. And then these are also the sites where the black holes are dramatically impacting the properties of the galaxies they live in. It affects the star formation rates of these galaxies, its color, its shape, and many properties. So even though the black hole is only a small part of the total mass budget of a galaxy, its environmental impact is quite large. So one would like to understand these interactions between black holes and galaxies. And also, as I mentioned, these most massive black holes are the best candidates for the Event Horizon Telescope because they have larger short radii, and the closer they are, the larger the angular size is. And I will talk about this at the end of the talk, is these most massive black holes are also potential sources of low-frequency gravitational waves. Here I'm talking about 1 to 10 nanohertz, much, much lower frequency than LIGO's range. But they have to be in binaries of the right orbital separations in order to be seen by these other experiments looking for nanohertz gravity waves. Okay, so these are just a partial list of reasons we would like to study these massive systems. So let me turn briefly to the topic of why had it taken 30 years to find these big black holes, right? You would think bigger things, bigger black holes have bigger sphere of influence, they got more gravity, they should be, bigger things should be easier to find, generally speaking. So why hadn't they been found? Okay, so there are two primary challenges for this type of observations. And I got started on this because of certain theoretical work I was working on with one of my prior students, a product of Berkeley physics, Mike Boylan-Colchin. In our simulations, we found certain predictions for massive black holes and galaxies that I was curious to know whether data supported or refuted our predictions. And this was in the mid-2000s, and I realized there were no data points at a very high mass end. And that's how I got into this observational campaign. I say, well, I might as well just get the data myself. And then I realized, wait a minute, there's a reason people didn't do this. And for reason number one is, obviously, massive objects are rare. This is just true in the universe. They're rare, then if you want to find the next massive galaxy, you got to look out further. Their densities are low, so massive galaxies tended to be further out. So to find big galaxies, which are potential hosts of big black holes, we do need to study, right? Black holes cannot be seen by definition, so we use stars orbiting very close to the black holes as dynamical tracers. So we need to be able to study the velocity of these stars within the black hole sphere of influence, so that the region within which the black hole's gravity dominates. Otherwise, you can't measure its mass. Okay? Just rough order of magnitude, the sphere of influence characteristic size within which the black hole's gravity dominates scales kind of like this. So for a 1 billion solar mass black hole in a galaxy with stellar velocity dispersion of about 300 kilometers per second, that's very typical of massive galaxies, the sphere of influence, the size is about 50 parsecs. Okay, now you put the 50 parsec at a distance of, say, 100 megaparsec, the Coma cluster, that subtends at 0.1 arcsecond on the sky. That is a very small angular scale, and the only way to resolve the scale is back then was to use a Hubble Space Telescope. And people had been very successful at measuring some of these, like M87 black holes, using the HST. So, okay, then why didn't they find 4889 or 1600? Then I realized, well, because they're really smart, okay? And let me just give you a sort of very brief analogy for this scale that you have to resolve with the Hubble telescope. Again, at 100 megaparsec, the Coma cluster, we need to resolve stars within, right, I say 50 parsec, it's about 1,000 light years located at this distance. And that scale, if I scale down the distance to the distance between San Francisco and LA, if I were to measure something in LA, it's analogous to trying to measure Yo-Yo Ma's fingers, how fast his fingers are moving while he's playing the flight of the bumblebee in the Disney Hall. Okay, so it's kind of difficult at this distance trying to measure how fast his hands are moving. Okay, and so that's why people use the Hubble Space Telescope. Okay, but that's only half of the problem. Then the more serious problem turned out to be that these giant galaxies I would like to target turn out to have extremely faint centers. Okay, and this plot shows you sort of what's happening here. So these are images taken of some of the many elliptical galaxies here, and the y-axis is the surface density of the stellar light in solar luminosities per parsec squared in physical units, and versus the distance from the center of each galaxy. So each curve is the surface density of a galaxy. And you can see that these blue curves are all run-of-the-mill elliptical galaxies, and they have these characteristic so-called Devockel-Bohr or Sirsic profiles. But these red ones I highlighted, you probably recognize some of the phone numbers now, they are actually much more luminous. They are the giant elliptical galaxies we are studying. And you can see the total luminosity, since the outer envelope is higher, the integrated luminosity is higher. But at a central few tens of hundreds of parsecs, the light flattens. There's this characteristic bend over, cores, we call cores. Okay, so in absolute numbers, there's basically a deficit of stars at the center of these galaxies. Ironically, they are overall more luminous, but at the center, they're devoid of stars. But because of these properties, why this happens is by itself a very interesting question. Okay, some people think it's a binary black hole core scouring, kicking out stars through gravitational slingshots. Okay, and therefore getting rid of the stars which would otherwise be there. Okay, that's by itself a good topic to study. But here I just want to highlight the fact is there is no light at the center. So it's very difficult to get spectra of these stars, which we need to study its velocities. That is to say, the Hubble Space Telescope is too small for these galaxies. You can't get enough signal to noise for the spectra. So it turned out that you really need 8 to 10 meter ground-based telescopes. But with Hubble's fantastic resolution in order to study these gigantic galaxies and the stars and to infer their black holes. So people were very smart to avoid these galaxies when they were using the Hubble. Okay, so it turned out that around 8 years ago, it became possible to use ground-based, these giant telescopes, but also with adaptive optics and integral field spectrographs, these fancy new instruments, to study these galaxies. So with the appropriate instruments on the ground, we realized that it's actually possible to go to this new era of post-HST black hole hunts. So that's when we started to collect data, and that's when I kind of became an observer. Okay, so our team had been using ground-based 10-meter telescopes with IFUs and so on. Of course, the next generation telescope will be even bigger light buckets, and will be able to study these fainter cores even more efficiently. Okay. So those are the two reasons why it has been so difficult. So let me just briefly mention now, so where are we in terms of hunting for these ultramassive black holes? Okay. So we found 4089, and there was other one we reported in 2011, and GC 1600, the one we reported earlier this year, was a result of the massive survey. So this is a survey I initiated about 3 years ago after having studied supermassive black holes for a while, realizing that, okay, we've looked at COMA, the biggest cluster, biggest galaxy out there. We've looked at a few obvious candidates, and it became clear about 3 years ago that we need to have a more systematic search for these biggest black holes. And so an obvious thing to do is, why don't we study the 100 most massive galaxies within sort of this distance within which we can resolve the sphere of influence of these big black holes? And turned out that these 100 massive galaxies hadn't been studied in very much detail, even though they are all well-known galaxies. Okay, so that's when we started the survey. And I will not go into details about this massive survey. The goals are, one, to study the supermassive black holes, but also we would like to understand the assembly history of how these most massive galaxies got to their current state, you know, how their symbiotic relationship with the black hole. So it's a broader survey of trying to understand both the black holes and its constituents, stars, dark matter profiles, and everything. Okay. So just for this talk, I want to just show a couple slides telling you briefly what we're trying to do here in addition to the black holes. Okay. And I just want to highlight that it has 5 core members of this massive survey, and then we have a number of offshoots involving different experts to study the molecular gas, for example, CO, carbon monoxide in these galaxies, warm ionized gas in these galaxies, the X-ray halo ionized gas, and radio and the initial mass function, which is a topic for another talk I will not get into here. Okay, but I want to highlight a contribution from 3 graduate students in physics here. Melanie, okay, is there, and Charles, there, okay, and Irina. Okay, and they're key members of this collaboration. And earlier on, I want to also highlight Ryan Janish, also from this department, also contributed to the early stage of our data analysis. Okay. So just the current status of the survey trying to study these 100 most massive galaxies, I just want to show you a little bit about the instruments we use. Okay. Again, the key is to get the stellar velocities, kinematics. So we combine wide field, integral field spectrograph. So here is a sort of publicity slide from the McDonald Mitchell Observatory showing this very wide field IFU, integral field spectrograph. So rather than getting a spectrum over a slit, in one shot, there are 250 fibers here. Each fiber gives you a spectrum for that part of the galaxy. And this is over 2 arc minutes, which is a very large field of view for a spectrograph. Okay, and we did the rest. So actually, for each galaxy, we have 700 spectra, and Melanie is absolute expert on the data now. Okay, so in one shot or a few shots, we get 700 spectra, allowing us to study what the stars are doing over a wide range of a given galaxy. Okay. But this is insufficient. This is good for studying stars and dark matter in the galaxy, but it's insufficient for studying the black holes because we need to resolve its sphere of influence. And just to remind you, each fiber is 4 arcsecond width. So that's very, very large compared to the 0.1 arcsecond I was talking about. So for the ones we want to follow up to study the black hole, in addition to other parts of the galaxy, we use Keck and Gemini, as I spoke. Basically, within that single fiber, we have additional expensive sort of observations to map out what the stars are doing with very, very fine angular resolution. And we combine all these spectra with a lot of information about what the stars are doing. We get the velocities, we get the dispersion, and we also get these deviations from the Gaussian distribution of the velocities of the stars to model what this galaxy as a whole is doing. Okay. And we also have accompanying photometry, so it's not just a spectroscopic survey, but also we need imaging of these galaxies. And for the very central part, as you saw, the core profile, light profiles, those are all obtained with HST. So HST is good enough for the photometry, but it's not good enough for getting the spectra. Okay. And so we have programs going on, and Charles is an expert on that. And we also have ground-based deep K-band imaging for those astronomers in the audience. This goes 3 magnitudes deeper than the 2MASS survey, so it allows us to study the stars and the spatial distribution of the galaxy to the outskirts very well. And we also have accompanying in other wavelengths observations going on. I want to highlight ALMA, the state-of-the-art radio observations that we have now found CO, carbon monoxide, at the centers of some of these galaxies. And ALMA has the spatial resolution to give us kinematics of what the gas is doing. And if the gas is regular enough in the form of a disk, then we can use that as a new tracer to measure the black hole mass as an independent measure. And we're pretty excited about that possibility right now. Okay. So I can go on and on about the massive survey, but I would like to move on telling you more about what we can learn from the data rather than the survey itself. Okay. So I would like now to turn, sort of putting things together. Okay, so sort of 2 major implications of the supermassive black hole studies are, 1, the scaling relations with galaxy, and 2 is the gravitational waves I mentioned earlier. So let me talk about the black hole galaxy correlation that I had mentioned briefly earlier. So this was around 2000. Two papers came out showing, and there have been a number of papers. One is by Hans-Walter Rix in the audience here. Okay, basically showing that bigger galaxies, however you measure it in the x-axis, host bigger black holes. And this is obviously a cartoon. Okay, and basically these are different types of galaxies, from spiral galaxies all the way to these spheroidal elliptical galaxies. But if you measure the sort of the spheroidal part of a galaxy, you can measure its mass, you can measure its luminosity, you can measure its velocity dispersion or some other quantities. You see this kind of very exciting correlation. And anytime you see a correlation, you try to come up with causality. Is it one causing the other to grow, or the other way around? There are a lot of theoretical debates about this, but the fact that bigger black holes live in bigger galaxies indicate that maybe they co-evolved. As galaxies merge together, the black holes merge, and somehow the food source made the black holes grow in bigger galaxies. So a lot of work, there's thousands and thousands of citations to these papers reporting these scaling relations. People are trying to understand what's going on. Of course, let me show you what the data are. Okay, as I mentioned earlier, the y-axis is from black hole masses, for black hole mass, and thus far only about 80 to 100 have been measured over sort of 3 decades of efforts, because it's very difficult to measure each one. You need a lot of data, as you've seen, and you need a lot of orbit modeling in order to tease out the black hole mass. Okay, I'm not going into the detail here. So real data kind of look like this. Okay, this is one of the most well-known M-sigma relation. Okay, so again, y-axis is the black hole mass measured dynamically from luminous tracers. Don't worry about the details here. There are different types of tracers marked here. But the x-axis in this particular plot is the velocity dispersion of the stars in that spheroidal component of the galaxy. It indicates how deep the potential, gravitational potential is of that galaxy. So you see, I just want to highlight, this is over 4.5 orders of magnitude in black hole mass. Okay, so this is 1 million solar mass, our little Milky Way, as I said earlier, is at the very, very low end of this plot. And the giant ones I talked about are up here. M87 is here, and the few up there. Okay, so you do see an overall trend. Okay, and the slope had been discussed to death. Is a black hole going like sigma to the 4th power, 5th power, and they have implications for the feedback of the black hole, how the black hole is influencing the galaxies. Okay, and these are different fits, which I won't go into details. But I want to now highlight the very high end. Okay, that 1600, the one we found earlier this year, is way up there. Okay, and the one we have not published and we are preparing right now is, if you recall, NGC 4874. That's the twin of 4889, and we have preliminary measurements now of this galaxy, and again, it's way off the relationship. Meaning, at the very high end, it appears that sigma, this long-cherished scaling relation, does not seem to be working very well. That is to say, sigma is not a very good predictor for black holes. Okay, and let me move on to the phone number. The last one is NGC 4874. Yes, and that's the second most luminous galaxy in the Coma cluster. And that's the one with the lowest surface brightness. So this one was really a pain to study. We had to sit on it forever to get enough signal to noise. There are just too few stars there. So thanks to Gemini, we got more than 10 hours of integration time on this galaxy. Okay. So let me show you another scaling relation. Again, the y-axis is the same, black hole mass. This is for a subset of the galaxies where the bulge masses are well defined. These are S0s or elliptical galaxies. Okay, and the x-axis is the stellar mass of that bulge component. So rather than sigma, I'm plotting the mass. And this relation had been established earlier, but these are the more recent data. Again, you see an overall pretty good relation, and we quantify the scatter. But I, again, want to highlight that 1600 is up there, and NGC 4874 is up there. And if you want to look at, you can ask, on average, what is the black hole mass relative to the galaxy mass, stellar mass? This mean relation is about 0.2% if you do a fit to this relation, okay, using 2013 data. This had been updated a bit lately, but these numbers hadn't changed too much. But 1600, the black hole is 10 times over massive compared to that mean relation. Why is that so? I don't know, but I think, but this is one fascinating thing about NGC 1600. And I want to, again, emphasize that it's not due to our selection effect. Okay, if the NGC 1600 were on this relation, we could have resolved it. We could have found it. So there's something that's making NGC 1600's black hole really voracious compared to its galaxy. Okay, I think this is for theorists to explain. Okay, just one thing, talking about theory, I want to mention that these scaling relations have been studied so much for various reasons. Okay, one is black hole masses are very difficult to measure, as you've seen, over many years of effort led to only, 100 points here. But the x-axis is much easier to measure. Okay, stellar mass, stellar mass is hard, but for other reasons we can talk about. But it's generally much easier to measure. Sigma, the velocity dispersion of a galaxy, is a standard thing any galaxy survey would try to measure, or luminosity, okay, of the galaxy. It's a Sloan Digital Sky Survey measurements of the x-axis. So the power of this relation is you can use all those measurements to infer, once you have these relationships, the black hole demographics over a cosmic history from redshift 5 to 0 when you have the galaxy information. Okay, so it allows you to study the black hole without actually having to measure individual black hole masses. Another reason this is useful is because I'll show you that the scatter about the mean relation is extremely important. Okay, it also tells us, in addition to the slope, how much scatter there is very useful. And here I'll give you one example of why it's useful. This plot shows a theoretical, very simple model that various people looked at, okay, in which they started out with, this is just a sort of numerical, analytical plus computer calculations. They started out with a seed of galaxies and black holes in each galaxy, where they put in absolutely no correlation between the black hole mass and the galaxy mass. Okay, it's random initially. And then they let their computer merge the galaxies. How you do that, you could use n-body simulation results, you could use merger rates. That part is understood very well. So they let their galaxies merge to form bigger galaxies in this computer calculation. And while the galaxy merge, they add up the individual black hole masses. Okay, so as galaxies merge, they found that obviously black holes get bigger, galaxies bulge masses get bigger. But you can see that as time went on, the scatter tightens at a high mass end due to central limit theorem. Okay, so this is a very striking result. All there is pure mergers, so no gas, but you just add. But their merger rates are quite realistic here compared to the lambda CDM model. Okay, it's taken from lambda CDM. So this is a very strong prediction of a pure merger model for growing black holes. Initially, there's no memory you get this result just through merger. But what we say is, as you saw from the previous slide, the observed scatter definitely doesn't tighten, right? In fact, it seems to be blowing up at the high mass end, meaning pure merger model cannot possibly explain the growth of, it's incomplete. Okay, so what we think would require, and that's not surprising at all, is late-time gas accretion, okay, from the gas. If you can funnel the gas toward the black hole, you need give you the stochasticity you need to widen the scatter. Okay, so this, for example, is something theorists can check. Can they produce this amount of scatter now we are measuring? Okay, so just give you an example of how these relationships can constrain models for growing black holes and their host galaxies. Okay, so now I have sort of messed up these well-known scaling relationships at the high mass end. That's kind of bad. So does it mean that we have no predictive powers at the high mass end now, right? Sigma doesn't seem to work very well. Bulge mass doesn't work. Luminosity doesn't work very well. So can we understand what's going on up there? Are there other properties we can correlate with? So it turned out that we were pretty excited with this. About this is, yes, we did find one parameter that the black hole mass correlates quite well with. And that comes back to this core. Okay, so again, the core radius, so this again is just Hubble Space Telescope images from of the, the central part of these galaxies. These are the surface brightness of these, the stars. Okay, and you can compute, you can fit a profile, Quasar, SIG, nuclear, whatever form you fit to these. There is a characteristic bend over radius, you see, for every galaxy. So for example, NGC 1600 has a giant core. It's about 2.3 arcseconds. Okay? So you can quantify that characteristic radius. And what happened was that radius turned out to be a much better predictor for the black hole mass, as I show you here. Okay, so this, again, y-axis is the black hole mass, and here we are limiting to the 20 black holes that have dynamical measurements that live in cored giant elliptical galaxies, that we actually have core radii measurements. Okay, and that's plotted in the x-axis. That's that bent over radius for each galaxy, right? This radius had nothing to do with the black hole as it's shown here, right? This is just based on photometry of the galaxy. You can determine that. But it turned out that this scatter is about 0.3 dec. It's pretty good for a characteristic, for a scaling relation. If you recall, by the way, this is the very high mass end. So this is not over 4.5 dec. This is only the highest. This is 1 billion, that's 10 billion solar masses. Okay, so if I were to zoom into the M sigma relation to this regime, as you remember, these black holes were all way above that relation. Okay, so this relation works much better. So another way to say this is we don't need spectroscopy anymore to get the sigma to predict black hole masses, but rather photometry. I'm not saying photometry is easier to get, but it's a different way. Okay, once you can measure the core radius, then you can actually predict the black hole mass. One other relation, the last relation I'll show, that we got really excited about is again related to the core radius of the galaxy. Okay, so the x-axis I'll keep the same for this sample of 20 core galaxies that we know of right now. But the y-axis now I'm going to plot another radius. Okay, in this case, this is the radius of the sphere of influence of the black hole. So rather than black hole mass, now in this plot I'm showing the radius of the sphere of influence. Okay, in actual definition, if you want to be mathematically correct, it's defined to be the radius within which the enclosed stellar mass equals that of the black hole. Further in, black hole wins. Further out, stars win. Okay, this is sort of a fairly arbitrary but natural definition of a characteristic radius physicists like to use. Okay, so we have dynamical modeling for all these black holes, so we can actually calculate what the sphere of influence of the black hole is. So that's y-axis. X-axis is just based on the HRSC photometry. And not only is the slope, best fit slope 1, meaning the two radii are proportional to each other, the more important part is the intercept is 1 also. So there's no offset in the two radii. Okay, meaning that the two radii are statistically consistent. Basically, they are equal to each other within the scatter. Okay, without any offset. So, and the intrinsic scatter is really small, 0.17 dec. Meaning, I think the implication here is that when you look at these cores, the cores are intimately related to the activity of the black hole. Okay, that is to say, I think the black holes are causing the cores. Now, what precise mechanism is causing the core, I'm not willing to bet yet. My collaborator Jens is convinced that that's due to core scouring I mentioned, two black holes spiraling, each other, kicking out stars and making these cores. I think AGN feedback, for example, if you can have activities not using black holes, but just blowing out gas, I'm challenging the simulators in the audience and the community to ask them, can you produce such observed correlation, not using binary black holes, but using AGN feedback? Because this is another example of observed scaling relations that can be used to confront theories. Right now, I don't know. Okay? But the fact that this is such a tight correlation is crying out for some explanation. And I think it's definitely the black holes are causing the cores. Okay, but the details still need to be sorted out. Okay, so those are sort of scaling relations right now for these massive black holes, the very massive end. Okay, so I'd like to turn the very sort of last 5 minutes to the last topic I'd like to touch on here, and that's the gravitational waves. Okay, so again, Professor Weiss showed this at his Segre lecture of the gravitational wave spectrum, the strain, dimensionless strain due to the gravity waves as a function of frequencies. And LIGOs are at the sort of 10, 100 hertz frequency range. And there is a space-based interferometers. Perhaps the ELISA have been launched that will be probing the lower frequency range. But I would like to talk about the pulsar timing arrays here, okay, because their primary sources are binary supermassive black holes of the kind I'm talking about. So I'm now an official member of the nanograph pulsar timing array. That's the American collaboration. There are 2 others in the world, one by Australians and one in Europe. 3 sets of international teams trying to use pulsars, millisecond pulsars, as their detectors to look for gravitational radiations from not stellar mass black holes, but supermassive black hole pairs. Okay, because the masses are so much bigger, the separations are bigger, it turned out that the gravitational waves are emitted at a much, much lower frequency, nanohertz range here. Okay, so I don't want to go into details about how the experiments are done. They're much, much cheaper relative to LIGO because pulsars are their detectors. And millisecond pulsars have been studied, have been known for over 3 decades. Okay, so but they can use collectively from the few dozen millisecond pulsars we know of in our galaxy, and from their arrival times, by correlating them and by studying the fluctuations in the arrival times to study the amount of gravitational waves that could be impacting the space-time between Earth and the pulsars and so on. Okay, that's the basic idea. And as you know, pulsars are very, very precise clocks, and that's why they can hope to detect this. But I just want to highlight now another paper I wrote last year with another physics student, Caitlin Schutt. And here I just want to show her beautiful plot. Okay, the sky location, this is in galactic coordinates, so this is the galaxy's plane, of the currently known millisecond pulsars. They're indicated by stars here. And nanograph is the North American team, PPTA is the Parkes Australian team by yellow stars, and the EPTA are the European pulsar timing arrays, and the red stars are the pulsars they are monitoring. Okay, some have been monitored over 30 years, some have been monitored over only a few years. And those are the sky locations, and in circles are the 80 plus known black holes that I showed you earlier on the M sigma relations. So those circles we have dynamical measurements. What we do not know is whether they're in binaries. Okay, we cannot tell. You can hide a binary within the sphere of influence. All we can measure is the total enclosed mass. Okay, that's making these stars move so fast. So that shows you the sky location of these supermassive black holes. Okay, so as it turned out that the pulsar timing experiments, they are most sensitive to the direction for a given pulsar. They're most sensitive to the line of sight right behind it. So the sensitivity is not uniform on the sky. The more pulsars you have in the sky, towards the sky location, the more sensitive they are to the gravitational waves emitted along its line of sight. Okay, so as a result, I will show you now in the same coordinate system, it's just a little different aspect ratios here, the latest upper limits on gravitational waves from supermassive black holes by these 2 experiments. Okay, this, as you can see, there's some sky variations. This part, they have more pulsars, so the sensitivity is a little low, better. Their upper limits is more stringent, okay, and you can see kind of a similar pattern for the nanograph 5-year data. But the overall sort of message I want to send is, right now they are putting upper limits on the sky averaged strain level of about 10 to the minus 14, okay, pretty stringent. And this is quoted at a given frequency. And as they monitor the millisecond pulsars longer, as they find more such sources, this limit is coming down. And the hope, of course, is one day we can detect gravitational waves. Okay, so just very quickly, so how is this relevant to the supermassive black holes I've been talking about? Well, I think the short answer is most massive black holes closer to the Earth are the best candidates. They will emit the strongest strain gravitational waves. And that's just because it's the last equation I'll show here, okay? Basically of this very simple equation, okay? This is the equation for the gravitational wave strain in terms of mass. You can see it scales like this mass to the 5/3 power and goes like 1 over the luminosity distance. Okay, so putting this equation in some useful units, you can see that for a source binary black hole at 10 megaparsecs, if its chirp mass is 1 billion, it's about 10 to the minus 14, sort of their upper limits. Okay, I'm just showing you sort of they are probing about the right range. And just as a reminder, chirp mass of a black hole binary is a combination of the two individual binary masses, M1, M2. Okay, in this definition, M1 is the bigger one. And you can rewrite this as the total mass times a factor that depends on the mass ratio of the binary. Okay. So here's the connection to our measurement. We are measuring dynamically the M total, as I said earlier. So there's this mass ratio which is uncertain here. It's very likely M87's black hole is actually a singlet rather than a twin. But we can use this, we don't know. Okay, we can't use astronomical measurements right now to determine X, but pulsar timing can tell us that. Okay, so this is one thing Caitlin calculated in our paper is given the black hole masses on that M sigma relation that we know, this is the total of the two if it had a binary black hole. Okay, this is the total mass versus the possible highest strain it could emit. If you look at this equation, this M is maximal when X is 1, and that's when they're equal mass. That is to say, for a given total mass, equal mass binary black hole gives you the largest strain. Okay, this is an optimal case. Of course, it's more likely that it doesn't have an equal mass black hole. Okay, but this is the optimal, maximal, or most optimistic prediction. And you can see here these top several, and again, these should be familiar phone numbers now, NGC 1600, NGC 4089. If they hosted a binary, equal mass binary, it would be producing strain that's already above the current upper limit. Okay, and the fact that they haven't seen any means that they can not harbor a equal mass black hole. Then you can reverse this argument and calculate what is the allowed upper limit on the black hole ratio. Okay, so for the hottest spots on the sky for gravitational waves, the limit is a few percent for the M2 to M1. So if 4089 had a binary, its secondary probably needs to be a few percent or less compared to its primary. Okay, this shows you already we can get some scientific information. The hope, of course, is as the massive team, our survey, start to discover more and more of these ultra massive black holes, since the strain scales like M to the 5/3, right? The more massive, the closer, the hotter the gravity waves will be, the higher the signal. We can tell the nanograph team where to look, and they can maximize their signal processing for maximal sensitivity toward those sky locations that we think could harbor massive black hole binaries. Okay. So let me summarize now. Okay, so we have uncovered a new population of ultramassive black holes beyond M87, beyond both, so by beyond, I mean both in terms of distance and in terms of masses. So we are, M87 is at 6 billion solar masses. So now we have 4 detected in the 10 to 20 billion solar mass range. Okay, and as I mentioned earlier, not all of them resided at the center of rich clusters. This is sort of the what people expected to find. Where are the biggest black holes? Well, they should be in the biggest galaxies. Where are the biggest galaxies? Well, they tended to be at the center of the richest clusters, like Coma, Virgo, right? And we had studied those galaxies. Now, through systematic search like the massive survey, NGC 1600 came out. We weren't targeting it. We wouldn't target it since it didn't live in a large cluster, right? But it is a massive enough galaxy to be in our massive survey. That's why we studied it. And as it turned out, it's the first extreme black hole discovered outside of a rich cluster. And all of these ultramassive black holes lie above the 2 well-established M-sigma relation and M-bulge relations for black hole galaxy correlations. And why that's so, I think is still open for discussion. And I want to highlight this core radius now as a new way to correlate black holes with the galaxies. And in particular, we're quite excited about these 2 radii being statistically indistinguishable, clearly trying to tell us something about the black hole activities and the centers of these galaxies. Okay, and how do we find more of these galaxies, right? What's our new hunting strategy? As I mentioned, the massive survey now gives us the candidate, very systematic, well-selected galaxy sample to study the black holes. And also, we are now using core size rather than sigma, which is what people used to do. People used to search for high velocity dispersion galaxies and try to study the black holes. As you see now, they don't correlate very well. So now we're using HST images, trying to determine the core sizes. And then these are probably much better indicators for where the massive black holes are. Okay, and the 2 sort of physics-related giant experiments going on, pulsar timing arrays and event horizon telescopes. Our candidates are probably, will provide them with the next targets to look at. Thank you very much.
We have time for a few questions. You can start off.
Your opinion is that possibly a supermassive black hole actually spits out stars, makes stars, and shoots them out. Are you aware of the work of Dr. Houghton Ark, the latest Houghton Ark? He proposes that some very massive, some kind of engine spits out entire seeds that evolve into galaxies, entire seeds of galaxies. What is Dr. Houghton Ark's work?
No, sorry, I don't know.
Yeah. Okay. Yep, he's very well known astronomer. So, can I?
Black holes will come back, or it will be a orbit.
Can I ask a question that surprised me on your? So the merger models, when they ended up correlated, the masses that ended up were orders of magnitude below what you're actually measuring. So is there a reason that the merger simulations were not producing the very high mass black holes?
I think there are probably 2 things. One is I'm not sure how realistic their time scale is. I'm not sure they really started out as well-defined redshift. Another thing is to probably more likely to gas companies. That new gas rather than merging to add to the black hole.
I see.
So not only would you add mass to the black hole, you add gas.
Right. There was I saw another hand back here. Yes.
This is with the HIT, we can go out to accelerate in kilovolts. So we can resolve, with HST, we can resolve to about 100 megavolts. Beyond that, I don't think we have to.
Our observation of the imaging of that is how large could be.
The black holes. Well, Peter just wrote a paper about that, right? So one thing to note is the galaxies don't get much bigger than 4889, basically. So unless you want the black hole to be half of the mass of the galaxy, which I think will be tremendously hard to do. The fact that you are running out of massive galaxies indicate that you're probably going to run out of very massive black holes, unless you've got some really weird way of feeding the black hole. So basically, the food source starts to run out. But there are many papers so far written about is there absolute upper limit on the black hole mass. And annoyingly, they always say 10 to the 11 or something, just a little bit beyond our number. And but I think the theoretical observations are very big. We're very much in the ballpark now. I mean, I have some very large core candidates I know of, right? Because we have the HST data. So we need to get the dynamical measurements. I think there may be a few out there of 20 to 30 billion, but probably not much.
So I saw two more hands. Get them, Dima, and then you.
Right, so the fact that it's a light bucket. Now, we are, one thing we are using is the GMOS spectrograph in natural seeing rather than adaptive optics sometimes. And the reason is adaptive optics on Gemini or Keck, it's extremely difficult to observe these galaxies because their centers are so thin. So TMT, when you have a much larger mirror, I mean, the signal to noise would just be incredibly much better. So we can probably integrate for just a few tens of minutes, and we can overwhelm the data quality over 10, 20 hours.
Last question.
So does this plot sort of suggest that the interaction between stars, black holes, is sort of problem?
The core cut problem of the dark matter?
Yeah.
Yeah, that is a very good question I didn't want to get into. Is when we are modeling these black holes, okay, the short orbit modeling, which I didn't talk about at all, we model the dark matter at the same time. And interestingly, like 4874, the short model, which is a fairly complicated model, wants a core dark matter also. And wants a core stars. So I think I think these big galaxies probably will have core. So that may be one way to look at that.
So I'm going to suggest we put up. If you have core questions, maybe you'll be willing to stick around for a few minutes. Yeah. Let's thank Professor Ma.